And we will start with the first speaker today in the session 4. This is Andreas Pütz from Ford Welke. Welcome on stage. You will talk about the scenario definitions for simulation use cases, and we are excited to hear about that. At set level, you are responsible for the development of reference scenarios, and today you will share your experiences and insights. We're looking forward to that. Welcome on stage.
Thank you. Thank you, Laura, for the kind introduction, and welcome everybody to the presentation on effective scenario definition for diverse simulation applications. Before I will start with the presentation, I would like to thank all of the colleagues, also the co-authors mentioned in here, for preparing this presentation and participating in the presentation preparation. So for the scenario-based testing, the scenario definition is an important element, and we would like to share our experiences that we have gathered in the past years within the set-level project. But let's start with an overview on the content of this presentation and how it's related to the overall content of the project. So on the left-hand side, you see that our work can be assigned to the model field in the set-level big picture. However, it has also quite close connection to the field of standards, since there were already existing standards for the scenario definition when the project started, like OpenScenario and also OpenDrive. But I will come to that in a minute. First, I will start with the motivation and the goals of this activity. And then the main part consists of 3 topics, which are the content structure, the technical implementation, and associated metadata for the scenario definition. In the end, I will close summarizing the lessons learned that we have shared also with the related standardization committees through the involvement of different set-level team members. So what was our motivation for trying to describe a scenario as effectively as possible? Since the Pegasus project, it is well accepted that the scenario-based testing is one of the key factors for the verification and validation of automated driving. And also working with scenarios on different abstraction levels, so meaning functional, abstract, logical, and concrete scenarios, is also well established by now. But in fact, there are more requirements on the scenario definition that originate from the use in different testing environments, so simulation, real testing, external loop, and so on. And also the high number of scenarios that need to be tested for an automated driving function. As a result, the scenario definition is subject to various requirements and therefore affects directly the testing efficiency. These various requirements can also be broken down for the set-level simulation use cases. As you can see here in this slide, the simulation use cases had also different interests in the scenario definition. While the criticality analysis was interested in being able to investigate the influence of an individual scenario parameter, the verification of the overall system was more looking for ways to describe certain aspects of a scenario in different levels of detail. The component simulation was again interested in the ability to describe material properties, an aspect that had not been in the focus before. At the same time, we wanted to use the same scenario definition for all of these use cases, and that's why we called them reference scenarios. Last but not least, as I said in the beginning, with OpenScenario, there was already an existing standard for the scenario definition when set-level started. Due to the fact that we obviously wanted to use and build upon this existing standard, we had to make sure that there was a mutual exchange between the standardization committee and our project. Only in this way it was possible that our development would benefit from the existing standards and vice versa. Now, before we could start with the technical implementation based on those aforementioned requirements, it made sense to take a look at the way how the content of a scenario can be structured. Here we could also benefit from the Pegasus project. The 6-layer model is well established and found its way into an ISO standard, namely 34502. Layer 1, 2, and 3 describe the static elements of the scenario, which are mainly described in the OpenDrive file. Within set level, we call these elements the traffic space. Layer 4, 5, and 6 describe the dynamic elements of the scenario and can be mostly found in the open scenario file. As you might know, Open Scenario has become an open ASAM standard, and we had a quite fruitful exchange with that standardization committee, as I said, through the involvement of different set-level team members. So we were quite lucky that we did not have to start from the green field. However, within our activities, we identified also needs for further development. As it was mentioned in the beginning, material properties, for example, were needed to provide input for sensor models on different abstraction levels. Not all of that can be supported by now. A second aspect that arises from the changed driving environment in comparison to the Pegasus project was the ability to model the timing of traffic light sequences. Even though those results from these experiences within set level have not yet found their way into an officially released standard, it is pretty clear that the gained knowledge will be used for standardization in future activities, so also after the project. Besides the 6-layer model that has been standardized, there were also existing standards, as I said, for the technical implementation when the project started, so meaning the early versions of Open Scenario and OpenDrive. As I mentioned before, the content of the scenario definition did not include things like material properties or also the detailed description of agent behavior. This means that from the perspective of the technical implementation, those elements needed to be added in the technical scenario description by using complementary files, so something like OpenCRG or OpenMaterial files. In addition, you see here in the table in the center of this slide that the existing standards like OpenScenario and OpenDrive might be well suited for describing concrete scenarios, but required some structural adaptations when to be used as scenario description on other abstraction levels. While functional and concrete and abstract scenarios are not in the focus of this standard, we especially worked on the possibility to implement logical scenarios within OpenScenario and OpenDrive. But due to the interdependency characteristic of a specific scenario parameter, it may be easier or harder to vary that parameter. So for example, while it's pretty easy to vary the speed of a traffic participant, it's hard to vary, for example, the curvature of the currently used road segment, at least if that road segment is part of a wider road network description. Some examples of concrete scenarios that have been used in the set level project as reference scenarios you can see here in this slide. You see that we had scenarios on different levels of complexity, which should facilitate the different needs of the simulation use cases. All of these scenarios, the documents on describing the content of the scenarios, as well as a technical implementation in OpenScenario and OpenDrive, can be found in our public GitLab. So I would like to encourage you to take a look at the material that is provided in the public GitLab. The provided scenarios and documents are all equipped with a pretty wide license file that allows for the use of these scenarios also in other contexts outside of set level. And if you are interested in more information, you will find more detailed description on the scenarios and the traffic spaces on the poster in our virtual exhibition. As I mentioned before, the implementation of a concrete scenario by the use of OpenScenario is pretty straightforward. But in scenario-based testing, also logical scenarios play an important role, since they give the possibility to explore or to test not only singular scenarios, but complete scenario or parameter spaces. So especially for the simulation-based testing and development, using logical scenarios is beneficial, since many scenario variants can be tested automatically in a fast way. When we started SetLevel, however, there was no existing solution for implementing a logical scenario. Therefore, we took a little detour by doing abstraction on a concrete scenario in a manual process. The resulting logical scenario was then handed over to the simulation framework, which used a script-based instantiation to automatically generate various concrete scenarios for the simulation. So in the beginning of the project, an XML scheme was used and implemented by Python expressions. It used UUIDs, which made reading the logical scenarios not really handy, we have to say. But over the progress of the project, the experiences were incorporated into the evolving standard ASAM OpenScenario 1.1. And due to the benefits of this new standard, we obviously used it in the remaining project duration. If you want to learn more about the standards that have been supported by the SetLevel development, I recommend the second presentation of the second session from yesterday, in which PMI showed a really nice overview on all the standards with SetLevel contribution. But we did not only gain knowledge in defining scenarios, so meaning the dynamic elements of the scenario. Also for the static elements described in the OpenDrive, a lot of experiences were made and found and will find their way into improved standards. At the beginning of the project, we decided to increase the complexity of the used traffic space over time. Therefore, you see here in the upper part of this slide a first simple intersection that was used also in the first half of the project. Due to its simplicity, so the orthogonal intersection arms, asymmetric layout, and so on, it could be easily implemented with tool support and required only very few manual changes. But this artificial intersection is not the reality, right? So we increased the complexity of the traffic space in the second half of the project and tried to create a so-called digital twin of the Forschungskreuzung in Braunschweig. This complex intersection with 4 arms and multiple lanes on each driving direction was equipped with various sensors by the DLR to be able to analyze the behavior of traffic participants on intersections. Even though the general tool support for creating this digital twin was quite good, it was necessary to manually model explicitly those things which make the reality trickier than artificial layout. In addition to the things that come from specific artifacts of the real environment, working with different tools on the same OpenDrive may also lead to issues. So for example, an intersection is modeled in OpenDrive as a road segment, which might not be the case for a proprietary definition within a specific tool. Here, an intersection may be also modeled as an open space, for example. These diverging approaches may lead to issues when tool A creates a traffic space in its own format, which is then exported into an OpenDrive and then imported into tool B and then transferred again back into a proprietary definition. While the execution might still be feasible in tool B, it's very likely that differences will occur due to different interpretations of the same elements of the OpenDrive file. So this non-native use of standard must be considered when working with different tools on the same OpenDrive file and should be overcome in the future. Something that might help on this end would be the creation of a catalog of reference implementations for some scenarios. In this way, questions regarding the interpretation of certain elements could be answered when implementing those elements. Something that is technically easier to solve, but has also many advantages for the scenario definition, is a complementation with metadata. A couple of advantages you see here on this slide. The first two refer to the possibility to search for suitable or used traffic spaces or scenarios in databases. So one example could be the traceability tool Tracey that was developed in Z-Level as well, and where we have seen the presentation in the first session this morning. But in addition to that, metadata can also help increasing the testing efficiency by allowing an automatic tool assembly or model assembly consisting of multiple elements. Especially when using test automation tools, automatic assembly is an important element. In general, metadata can help exchanging information on traffic spaces and scenarios also over organizational boundaries. So for example, when an OEM provides a specific scenario to a sensor supplier to simulate the capabilities of the sensor in this specific scenario. Within Z-Level, we clustered this metadata into three main groups. So the descriptive metadata contains information like who created the model and might be the contact person in case of questions, for what is the traffic space or the scenario suited, so meaning what is the quality of the models and so on, but obviously also information describing the content of the scenario. Does it contain an intersection or what type of traffic participants are included in the scenario? The structural metadata is more focused on the related hierarchy that the OpenDrive and OpenScenario file might be part of, and is therefore especially important when using automatic model assembly. The third group is administrative metadata. Things like timestamps of last modification or release status of artifacts or their type are summarized in this group. If you take a look at the item artifact type, you see that traffic spaces and scenarios are not the only ones that are mentioned in here. This is due to the fact that we used the same format as for other artifacts like simulation models to keep the metadata consistent across various elements that are required for conducting a comprehensive simulation. The format that we have chosen to use is SRMD, so the acronym for Simulation Resource Metadata. You can find a format description as well in the public GitLab if you want to understand this XML-based scheme a little bit better. You will also find some SRMD examples for our reference scenarios that I have described in the beginning of the scenario, or you take a look at the booth where the metadata is also described. That brings me to the end of this presentation, and I would like to summarize our findings from working with traffic spaces and scenarios. First of all, I would like to highlight again that the gathered insights have found their way into the related standardization committees through the involvement of different Z-Level team members. However, there's still work to be done. For example, in the definition of a standard, it is very helpful. The definition is helpful, but leaves sometimes room for interpretation of certain aspects. And this room for interpretation may in return lead, as I said, to diverging results when using the same scenario on different tools. A reference implementation could help to overcome this issue. A second aspect that has room for improvement is the definition of material properties to be used as input for sensor models. The best technical solution for the integration into the scenario definition has still to be found. The last aspect refers to the possibility to vary static scenario parameters of the static scenario description. in a logical scenario way. Here, I would like to motivate you to take a look at the work of Daniel Becker on the road generation tool that shows one approach how to address this issue. In general, I hope that you will use the opportunity to check out the material on traffic spaces and reference scenarios that is publicly available in the GitLab. With that, I would like to thank you for your attention. I'm looking forward to any questions that you might have.
And I'm sure there will be. Thank you very much, Andreas Pütz, for the support. And this is your first applause. Thank you so much.